Okay, next is heat maps, and heat map is particularly useful for studying correlations. Okay. So you have a bunch of variables and you want to study the correlation among those different variables. Okay. When you have lots of predictor variables, okay, we're going to discuss this more in next chapter. So if the predictors are correlated among each other, okay, and that is called multicollinearity, which is not good because they are trying to compete with each other in predicting the target, and when you do that and they both bring each other down, and you don't get very reliable predictions. So if two variables are very highly correlated, you want to get rid of one of them. Okay, you don't want to get rid of both of them. We do want the predictive power, but we don't want competition between the predictors themselves. So it is important for us to study the correlations among a set of variables, and heat map is a very nice visual way of looking at where the high correlations are there and where the correlations are not high, which is good, right? So heat maps bring out high correlation. So graphical display of numerical data where color is used to denote the values, the intensity, the magnitude of values. Color-coded values are easier and faster to comprehend, of course, useful in examining large number of values and visualizing. There are two applications that's highlighted here. Visualizing correlations and then visualizing missing values. So you can plot missing values as a heat map, and then if the missing values are all over the place, you will not see very much, which is okay. But if the missing values are concentrated in some particular range of columns and particular range of rows, then you'll see a large gap in the heat map. Then you will be able to study that and see why is that a problem, why there is so much of missing values in that one particular region, and is there a way to mitigate that and that kind of stuff. So these are the two main applications for heat maps. Okay. All right. So first we're going to look at examples of both of them. Okay. This is correlation. So first thing is correlation. Correlation table for p variables has p rows and p columns and so on, right? Okay. Heat map for housing data. All right. So okay. So we're going to now prepare data for correlation, okay? Because correlation is only for numerical variables. So if you have factor variables or character variables, we need to remove them. Okay. So in this case, we have Chaz, which is a character, which is a factor variable because it's 0 or 1, right? Adjacent to Charles River or not. And then there is cat med v, category of med v, which is 30,000 or less property value will be 0 and or 0 or 1 or 0 for 30,000 as the property value. So those two are not numerical variables. So we can't compute correlations for that. Even if you compute correlation, because they are coded as numbers, you may be able to compute correlation, but they won't mean anything. So we don't want them. So what we are going to do is we're going to do a subset. So we are going to gather the columns, okay, except for those two. So, and you can do that with subset. Subsets columns, right? So subset from where? So from housing.df, okay, and then we say select. Okay. Now we're going to say what we don't want to select with a C, minus C, sorry. So we say don't select Chaz and don't select medv. Okay. So that's going to select all the columns but get rid of those two. Chaz and medv, cat medv will be gone, and then the function is just COR for correlation. Correlation, well, here, there is one, okay, I'll talk about that in just a second. Data for okay. I have a dot here, that's not right. Okay, so here is our correlation. Okay. Now we have MET-V as well, okay, but we must remember that correlation, MET-V being the target, correlation with MET-V is good. Okay, it is correlation among the predictors that's a problem. Okay, so we have both the target and all the predictors, so we have to keep that in mind. Now we want to, instead of numbers, we want to plot this, okay, such that larger values either on the positive or the negative side, because correlations can be both positive or it could be negative. So any value that is closer to 1 to have a higher level of intensity, and values that are closer to 0, lower level of intensity. That's what heat map is. Based on the values, you color code. Smaller value, you use lighter colors, and larger values, you use more intense colors. Okay? So that's what we want to do, but so first thing to do is to save this. Okay? So we need to save this into a variable. So now we have the correlations, but the correlations, okay, to plot them as a heat map, okay, we have to have correlations in a different form, not as a matrix like what we just saw, not like this. What we want to be able to use in ggplot, we need to have 3 columns. Okay? All of these correlations must be melted down in a sense. So it will have variable 1, variable 2, and its correlation. And then variable 1, variable 2, its correlation. So we need 3 columns. Okay. One column will have the first variable. Okay, so here we have 2-dimensional matrix, right? So you have one variable coming from the rows, one variable coming from the columns, and at each intersection you have a correlation. And for us to plot this as a heat map, those values must be in a table form. First variable, second variable, its correlation. First variable, second variable's correlation, like that. So this is called melting. You take this matrix and melt it down into 3 columns of data, and that melting is done using another library, right? And once again, I don't think that library is here. Let me see. Library Reshape. Reshape 2, actually. So let's install Reshape 2. And Reshape 2 is used to melt matrix data into 3 columns of data. Okay, once that is done, then run Reshape 2. So this feature is what makes R very powerful, because for just about anything you want to do, there is some library out there. Okay, so you have to Google for it, and how do you do this, and then it's okay. Here is a library, and you do this, and you get it. Okay, so that's the power of this is true with Python also. Okay, they both have a large repertoire of libraries that does anything you can imagine. Okay, so so now we have, let's recall, we need to save this melted correlation, right? Then you say melt. Well, melt correlation matrix. Okay, so which is core matrix is the name that under which we save the correlations. So you say just melt. Okay, since we have only 2 dimensions here, this melt will work. But you can do melt with the larger data where you want to select just 2 or 3 columns and do melt. You can do that too. Okay, so it's a little more involved. But here we will use the simple syntax. So now we have the melted correlation. So you see there are 114 observations. So each line is a pair of variables and the corresponding correlation. Of course, when you have a variable the correlation of a variable with itself is going to be 1. And that's what's going to be in the diagonal. Okay? So you have the variables and you have the values. So now you can use var1 on the x-axis, var2 on the y-axis. Okay? So that will then bring you that 11 or 12 values on the x-axis and 11 or 12 values on the y-axis. So it will be like a matrix. And then you will plot these values, but you will plot based on the value, you will apply a background color.